Okay, here's my second part of my series on the Newton-Raphson method and how you can approximate answers to any functions, solutions of any function of any kind using what we call the Newton method or sometimes the Newton-Raphson method. And in the last video, what we did is we used a familiar function, x squared, and we wanted to approximate the square root of a function, basically. And this one, we're going to use one that's a little more difficult to do just because there's not a standard key on a calculator or a standard function that we can solve to solve this kind of equation, x to the x equals 10. There's no really easy way to do this. So what we're going to have to use is some kind of really good approximation method, and the Newton's method is a great one for doing that. So we're going to go through this example, and I'm also going to show you how you could program the Newton method into a spreadsheet program to continue iterating this process and generate even better answers. Again, this is something I haven't done, but it's not too difficult, so we'll do it on the fly here. So let's suppose we had a function x to the x. This works for any kind of function, as we said last time, but x to the x equals 10, and we wanted to know what x solves or what x satisfies this equation. So down here we have a plot of x to the x from 0 to 3. And what you see here is it dips down, starts close to 1 and dips down and then goes back up. And after x gets bigger than 1, when x equals 1, y equals 1, because x 1 to the first power equals 1. And from there it continues to get steeper and steeper and steeper and steeper. Here's a little zoom in of x to the x from 0 to 1, and we see that when you get close, x gets close to 0, x to the x gets close to 1, and then it dips down close to about 0.7 or so at a minimum, and then at around 0.3 something it turns around and starts heading back up. And so if we want to solve this for x to the x equals 10, if we look at this graph, I have marked over here a green dot at approximately where x to the x equals 10. And if we look down here at the x-axis, we can see that the answer we're looking for is somewhere in the neighborhood of 2.5. But suppose we need a very, very precise solution for what x to the x, what number x, when raised to itself, equals 10 for some reason. Let's use the Newton method to do that. So here are the same steps we went through in the last video. For any function, f of x equals y. So here, f of x is x to the x. Y is 10. Make an initial guess, and then plug it into the function. Make a second guess that you think might be a little better. Doesn't have to necessarily be better, but it's the method works better if it's better. Some number kind of close to your original guess, and then plug that into your function. Calculate this number r, and remember the r is a slope, and we'll look at this graphically again here just to see how it's working. And then we plug that r into this function to get an even better guess. So let's just get started and let's go through the process here. And while we're doing this, I'm going to plug in some of these numbers and some of these calculations into a spreadsheet. You can use Excel or whatever you want. These days I prefer to use LibreOffice just because it's free and it's very good. I've been doing some work in LibreOffice Portable. It's a version that just runs off of a pen drive, and I found that sometimes it is more robust and easier and crashes less often with big data sets than Excel does. So that was a very nice surprise. So here I've set up the spreadsheet with f of x. Now this isn't going to do anything. This is just for our reference. Is x to the x, that's the function. The y value is 10. And what we're going to do is come up with an initial guess, plug the guess in because that's what the algorithm says to do. And then we're going to calculate this number r for our two guesses. So it requires two initial guesses. So we have our graph here, and we could use our graph to help us form an initial guess, but we don't even have to do that. Let's just do this. Suppose we didn't know what the graph even looked like, and we just had to sit down with a piece of paper and do this, or a spreadsheet and do this without a graph. What would you do? What would your initial guess be for x to the x equals 10? Well, let's just start plugging in numbers we know. Try 1. Well, 1 to the 1 power is 1. That's not really close to 10. Let's try 2. 2 squared equals 4. Well, that's getting a little closer. What about 3? 3 to the 3rd power equals 27. Well, that's a little further off even than trying 2 squared. So how about we make our initial guess 2? So what we're saying is our initial guess 2 is what we're going to call x0, or x0, as some people will call it. So let's make an initial guess 2 and plug 2 into this formula. 2 squared equals 4. Great. Now, we need to make a second guess. So, when we tried 2 squared, that gave us 4. When we tried 3 squared, that gave us something much bigger than 10, 27. So let's try something just a little bit bigger than 2. What do you want to try? 2.1? 2.2? Let's try 2.2, just for fun. Now let's check our graph. Let's use 2.2 regardless, but let's just look at our graph and see if that's going to be close. Now if we look at our graph, the answer looks like it's going to be somewhere around 2.5. Well, let's ignore that. Let's suppose we didn't even know that. Let's just go with our guess, our second guess. Here is 2.2. The point is that your guesses don't have to be extremely close to the real answer. But we're going to keep getting closer and closer to the answer as we do this. So let's plug this into our formula. Let's put in a little formula into LibreOffice here, kind of like you would in Excel, equals whatever's in that cell raised to the power of whatever's in that cell. Okay, and we get a number 5.666695779. It's not real close to that number 10 there. So even though that's not very close, let's use it anyway, and let's just go through the Newton method process, and we'll go through this process 2 or 3 times until we get an answer that gives us an output, a number really close to 10 when we raise it to its own power. So once we have our initial guess, here, let me actually insert a column here so we can, if you're not used to Newton's method or you're a little rusty on it, this is what we call our x0, our initial guess. This is what we call x1, maybe a little bit better guess. And then, using Newton method, let's just review the formula over here. Again, if you didn't watch the previous video, please go to my website, www.berkeyacademy.com, and download this worksheet here. I will also put this Excel spreadsheet on my website there. You just go to my website, click on Files, and this worksheet right here is going to be called Newton1.pdf. And I'll call this little spreadsheet Newton1.xls or something. I'll save it in an Excel format for you. So the Newton method says make an initial guess, plug it in to the function. Make a second guess, plug it into the function. So we've done those two things. Now we calculate this number r, and r just says take the difference between the two outputs of what happens when you plug those two numbers into the function. So f of x1 minus f of x0, and then divide that by the difference between your better guess and your initial guess. So better output minus initial output better guess minus initial guess. Divide it by those two. So let me just put that function in here in a spreadsheet right here for R. And I'll say, okay, this is going to be equals. So this is right here, the 5.666 is our better output minus our initial guess output divided by parentheses better guess minus initial guess. All right, so we have this R, 8.333478894. Now let's go through and calculate our better estimate here. And then we're going to iterate through this a few times, do the same thing again and again until we get a very accurate estimate for the solution to our function. So let's see what our better estimate is and see how close it is. So the last step in the Newton method says calculate our better estimate. Shouldn't call this a guess, but a better estimate will be take the last estimate, x1, add to it y minus f of x1 over r. So let me, here I will move this spreadsheet over here so where we can see both the spreadsheet and that function here. So an even better guess is take the slightly better guess, the x1 here, which is 2.2. Let me just stretch that down a little bit. Plus y, which is 10, minus this little bit better output, 5.6669, over the number r. So let's put in a little formula here to do that. Equals x1, 2.2, plus parentheses y, which is 10, minus f of x1, okay, that's that one, divided by r. Enter. So this is telling us our better estimate of what number, when you raise it to itself, will equal 10 is 2.7199874238. Okay, so now let's do this whole thing again using this better estimate. And let's call this better estimate x2, just like we had on the worksheet down here. But we're gonna iterate through the same process again. Let me just copy that number over here. And let me paste only the number. Okay. And now let's copy this formula down. And so what happens when we raise 2.719987 to itself? We get a number 15, which is too big, because what we're shooting for is 10. So let's go through and iterate this process again and see if we can come up with a better number for x to plug in here. So what we have to do is calculate another r. Now hopefully I've put in this formula to where if I copy the formula down, it will just update the formula. But what we're going to do is we're going to, let me move this up a little bit. So what we're going to do is calculate a new version of r using our best estimate minus our next best estimate. Well, what happens when you plug it into x to the x formula? So this is the number that was about 15. This is the last one that was 5.6. And we're going to divide that by our last estimate, which is about 2.7 minus the previous estimate before that, 2.2, the previous best estimate. So let's bring that Excel spreadsheet up again and let's go through one more iteration. So now R says is about 18, and we'll interpret what these slopes are doing in just a few minutes. We'll go back down to this this graph and see what all this is doing. Now let's calculate a better estimate. So our better estimate is going to be take the previous best estimate, 2.7, and we're going to adjust it. We're going to add 10, the y, minus f of x1 divided by r. So 10 minus f of x1, well now it's f of x2 though, divided by the new r. So let me copy this formula down, and then let me double check to make sure that it's doing the right thing. It's giving us a better estimate now of 2.436. And so that does look like it's getting closer to what the graph is suggesting, a number of about 2.5. Let's iterate again. And let's just keep doing this several times in a row here. We can kind of automate this. So x3, x4, x5. And let's just keep doing this. So we're going to do this sort of automated. So let me copy this. And then I'm going to paste it. I'll do this part manually. And now let's copy down this formula. So now if we plug in 2.436 raised to itself, we're getting 8.7. We're getting a little closer to that 10. And now if we iterate through Newton's method again and we calculate a new r, 22, we calculate an even better estimate, 2.49. Okay, let's copy that. And let's paste it. And let's see how close we are. Whoop. Paste only the number. Let's see how close we are when we raise 2.49 to the 2.49. Ooh, we're getting pretty close now. Let's run through Newton's method again. Another r. Another better estimate. 2.507. Okay, let's copy that. And let's paste the number. Let's raise it to itself. Ooh, very close, 10.022. And let's calculate another r. Let's calculate an even better estimate. So again, you can write programs, and this is what calculators do for a lot of different situations. They run through an algorithm just like this, but they do it so fast that you don't even notice that it's happening. And now let's just go through this 2 more times and just see how accurate we can get this. So let's copy, paste. Whoop, sorry, I have to paste the number only instead of the formula. All right, raise it to itself. Ooh, 9.999, getting very close there. Okay, so let's run it through one more iteration, and I think we're going to find that we're going to be getting an answer that's so close that we might just be happy with it, because we're sort of converging here. So let's see, copy, paste only the number. Oh, 9.999999561. We're getting really close. And so again, you can keep iterating this until you get as close as you want. Oh, just for fun, let's go through one last iteration. But you see, each successive time we iterate through, our next best guess is not changing hardly at all now. And so this is when you write a computer program, or you wanted to program a calculator. Someone had to program these for the first time. Normally what people do is they say, well, keep running through an algorithm like this until the difference between successive estimations, the difference between them is tiny. And you can define tiny to be whatever you want, but you see here the difference. There's no difference down to the 1, 2, 3, 4, 5, 6, 7. Down to the 8th decimal place, there's no difference, or the 7th. The 8th is the first difference. But let's do this just one last time to see how ridiculously close this is going to be. So let's see, copy, and paste the number. Oh, look, it rounded it off to 10. Now, that's not exactly 10. If we actually have it display this to enough decimal places, it won't be 10. Here, let me expand the decimal places. So look at that. I had to expand this to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 decimal places until the spreadsheet program gives us anything different from just the number 10. And so for most purposes, this might be accurate enough for us to where we just stop. And so what is our answer, our best, our approximation? Again, this is not the exact answer, but this is close. Of what number raised to itself equals 10. This is pretty good. And again, we could keep making this better by iterating through. Let's look at the method one more time on the graph to see exactly what is going on, because this is, I think, more important than using a method is understanding the method, of course. So let's see what happened during the first couple of rounds here as we use this method. Our first guess was 2. So let me go over here and let's look at this graph and zoom in here and see what's going on. So let me label things real quickly. Alright, so here I've zoomed in on the graph and gotten some of the initial points labeled, and over here we're looking at our numbers from our Excel worksheet too, so we can graph them pretty quickly as we go here. So the blue point here was our initial guess of 2, and 2 squared is 4. We made a little bit better guess of 2.2, and then we found out that 2.2 raised to the 2.2 is 5.66696, and so that's this green point right here. So what Newton's method does, and what this R number is, as we talked about in a previous video, is R is trying to calculate the slope between the blue and the green point. And so it's telling us that the slope between those 2 points right there is about 8.333. So let me make that a little transparent so we can see what's going on behind it there. So the yellow line segment has a slope of about 8.333. Now, what we do to get this better estimate of 2.71 is the Newton method says, well, let's take the distance between this best guess so far, 2.2. When we raise it to itself, we get only 5.667. Let's see how far the distance is between that point and 10. So that formula says, let me make this, I'll make this little line segment in yellow also, so we know that this goes with the same sort of step. All right, so there's yellow. So to calculate that better estimate, what we do is we say, well, what we need to do to get to that red point is we need to somehow go up another between 5.6 and 10. So we need to go up about another 4.5, a little less than 4.5. So if we're going to go up another 4.5, but we're going to keep doing it at this slope of this segment right here, then what we're going to have to do is draw a line segment with that same slope as that yellow, but extend it out until we get that much higher. And so let's let me make this red here, but a little transparent so we can see where it overlaps the original one. So this orange line segment is the original one that we were using the slope to get the slope of 8.33. But what Newton's method says, we know that we're this far off, about 4.4 off. So let's extend this line up until it goes up another 4.5, and let's see what value for x that gives us. And so this better estimate is that number, 2.71. So we've extended our line out here. So yeah, I didn't use exactly the same slope there, but you get the idea. So we use that as our next starting point, our best guess. But when we plug that into the function, we're way off again. So we plugged the 2.71, 2.7199 raised to itself, we get 15.20. And so why are we so far off? Well, because that takes us up here, way up there, to this point. Oh, I'll give it a purple color here. Okay, so now we're way up here, we're way off. But the method is still going to help us zoom in, because the method's going to recognize that we overshot, and it's going to help us backpedal and get closer to our target. Well, how did it do that? It said, well, let's take this new estimate. We get the 15.20. Whoops, we overshot by 5.2. We're actually a little closer to 10 than we were. We were 5.4 off. Now we're only 5.2 off, even though it looks like we're far away. Now let's calculate the slope between the where we want to go and the purple point. And so, well, actually, sorry, that's not what we do. We calculate the slope between the purple point and the last best estimate. Sorry for misspeaking there. And so let's see what that slope would look like. Let me draw a line between here. So it says, let's look at this best estimate. Sorry. This best estimate and the last best estimate. And let's calculate the slope between those 2 points. Well, this slope is a lot flatter than a lot steeper than the last one. This one was flat at 8.33. This black line is much steeper. The slope is 18.34. So we're going to use that slope as the basis for calculating a new estimate. So how do we do it? Well, we start with our purple point, our 2.71 estimate or 2.72 estimate, and then we're going to backtrack. Using this slope, we're going to backtrack until we go down. So what do? Well, we find out how far we are off. I know this is getting boring, but hopefully this is helping you. So we calculate how far we are off between the 15.2 and the 10 here. So let's see. Okay. And we see that that's how far we off. So what do we want to do? Well, we want to backtrack along this black line until we get back down the same distance. But we're not really traveling along this curve, we're traveling along the black line. So the function is telling us to start at the purple point and go down until we go down the same distance. But we're traveling along that black line here, so let's make that into a greenish color here. And where do we end up? Well, where we're going to end up is an estimate of about 2.4. And so our new best estimate here is 2.43. So that's our new best estimate. So let me put a little circle there. I'll recycle yellow. Running out of good, bright, visible colors to see. So that's our new best estimate. But then when we plug it into our equation, 2.436 raised to the 2.436 gives us 8.7. So we're down here. But we're getting closer each time. We're zooming in a little bit closer as we bounce back and forth and bounce and back and forth. And then what we do this time is we look at the slope between this estimate and the purple estimate. And then we backtrack. And we keep bouncing back and forth until we get closer and closer. We keep zooming in every time to our final answer. And as we saw from our Excel spreadsheet, we can get, as we say in the business, arbitrarily close, which means we can get as close as we want to our solution. So I guess if I kept going, I would just be repeating myself again and again. let me end the video here. If you have any questions or comments, please leave them in the comment section below, and I will post these files to my website at www.berkeyacademy.com under Files, and I will name them Newton something, so they'll be easy to find. So please let me know if you have any questions. I hope that this has helped you understand what the Newton method does a little bit. Thanks and good luck.